In the last material and energy balances video, we discussed single component equilibrium. And this can help explain why we still feel humidity even when the ambient temperature is less than the boiling point of water. Today, I'm going to extend that analysis to multi-component phase equilibrium, specifically how Raoult's law can apply for multi-component systems. And this is important because this is one of the key ways that chemical engineers that are in industry separate liquid mixtures. So imagine that you had a liquid mixture of two components and you wanted to separate those two components. The most common way that this is done is by bringing it to a state of phase equilibrium. In other words, what I'm going to want to do is vaporize some of it or bring it to a partial boil such that vapor and liquid are coexisting in the same system. The magic of this method is that in general, the vapor phase is going to have a different composition than the liquid phase. So when we make a vapor out of this initial mixture of two components, my vapor now has more red molecules than gold molecules. And after you have phase equilibrium, a vapor is very easy to separate from a liquid. You would just draw a pipe off the top, and then you can go collect this later in a condenser to achieve your separated product. So as the engineer, what your job is to be figuring out what process conditions, temperature and pressure you need to set in order to get a certain composition that you desire. In order to do this, again, we can do Gibbs phase rule. So starting with Gibbs phase rule is always a good place to start for these types of problems. Remember that again, Gibbs phase rule is 2 plus components minus number of phases minus reactions, which is 0. And in this example, I have two components again, gold and red, and two phases, which are vapor and liquid, meaning I have two intensive variables that I need to specify. Now remember, in the single component Raoult's law case, or the single component phase equilibrium, my choices were temperature, pressure, and vapor phase composition. Now that I have two condensable components, or two components that can exist in the liquid phase, I have to add X, the liquid phase composition. So once again, the implication of Gibbs phase rule equaling 2 means that if I set any two of these variables, then the other two will be set by relationships. So for example, if I had a particular vapor phase composition and liquid phase composition that I were striving to achieve, I could then, with equations and with Y and X set, I could calculate what the temperature and pressure ought to be in order to get that to occur. Similarly, if I had a certain temperature and pressure that I wanted to run, I could predict what the vapor phase composition and what the liquid phase composition would be. Once again, the relationship between these intensive variables is going to be Raoult's law. And it is going to look similar to the form of Raoult's law that I had for a single condensable component, but there's one minor change. Raoult's law for multiple condensable components. And just as a reminder, last time there was a single condensable component, but two components overall, because we had air as one of the components. And air cannot condense at ambient conditions. And the difference here is that we've replaced air, so there's no air in the system. I don't think I've mentioned that. So this currently would be a vacuum in the headspace, or once the vapor phase is established, there is no air molecules in there. So Raoult's law for multiple condensable components looks like so. It is Yi times the pressure, and once again, remember that is equal to the partial pressure. Get very clear would be my recommendation about the difference between partial pressure and vapor pressure. Partial pressure is the mole fraction in the vapor phase times the total pressure. You can think of it also as the fraction of the pressure that is exerted by the molecules of any specific component. So each molecule in the vapor phase is going to exert a certain amount of pressure that will total the total pressure. So just like the sum of the Yi's, the vapor phase mole fractions, has to equal 1, the sum of the partial pressures has to equal the total pressure. Then by Raoult's law, this is equal to Xi, so that's the liquid phase composition, times the vapor pressure of component I. And remember, this is as a function of T. This does not So the way Raoult's law can help solve this problem is that you can write a Raoult's law expression for each component in the system. So let's say I have red and gold, though I'm just going to call those my two components. I can write a Raoult's law for each one. So therefore, Y red times total pressure is equal to X red times the vapor pressure of red at the temperature T. I can also write a Raoult's law for gold. Y gold times total pressure is equal to X gold times P star gold at that system temperature T. And then I have relationships that I can write. So I have physical constraints. I can say Y red plus Y gold is equal to 1. And X should be a red, should be an R, not a P. X red times X gold is equal to 1. Do not say this is a physical constraint. So this is something I see every semester. This is another common mistake. Students write X red plus Y red is equal to 1. This is not the case. This is not the physical constraint. The physical constraint only applies to mole fractions in the same phase. So the same phase means that Y is both representing the vapor phase, X is both representing the liquid phase. I cannot mix a mole fraction from the vapor and liquid phases and say that is equal to 1. All right, so with these relationships, I could substitute one or the other. So instead of saying Y gold, I can say 1 minus Y red. That's the same thing as saying Y gold times P is equal to 1 minus X red times P gold of T. So I'm just substituting my two variables here to make it such that I have 4 equations, 4 unknowns. 4 unknowns, and remember I have to have 2 of them specified. So my unknowns are going to be Y red, P, X red, and T. And the same 4 variables are in both equations now. So therefore, if I had set 2 of them, so setting 2 out of the 4, then I could use these 2 expressions to solve for the other 2. This video is almost over, but before I wrap this one up, I also want to mention the cousin, is what I call this, of Raoult's law, Henry's law, which may be more appropriate for very dilute solutions. So Henry's law. And Henry's law has a very similar form to Raoult's law. The only difference is that the vapor pressure is replaced by Henry's law constant. So Henry's law goes Yi times P, so same exact left-hand side, is equal to XA times, instead of P star, this is HA of T, where HA is Henry's law constant. And this parentheses T, again, reflects that Henry's law constant is a function of temperature. Henry's law constant for component A at temperature T. And you'd have to be given what Henry's law constant is, or you'd have to look it up on the internet. There's several resources that you can use to find Henry's law constants. I don't think these are in the book, but I could be mistaken. Definitely vapor pressure, I think I'll mention again, for vapor pressures, you would use Antoine's equation. And for that, I've spoke about that multiple times, but you would look in Appendix B4 or NIST.gov to find those Antoine's constants to use Antoine's equation. And to wrap up this video, I had one final thought that I wanted to stress, was that the definitions of Raoult's law and Henry's law that I've given you here are valid only for ideal mixtures. And once again, for this class, we're only going to assume ideal mixtures. Don't mix up ideal mixtures with ideal gases. So an ideal mixture is one where the properties can usually be seen as a weighted average. So the property of the mixture is equal to a weighted average of all those individual component properties weighted by the composition of that mixture. Later on in the curriculum, in a future class, you'll learn the more general form of Raoult's law, for sure, that take non-idealities into account. So certain mixtures, like water and ethanol, is a classic one that does not behave ideally. This form of Raoult's law is not valid for it. So just keep in mind that while this is going to be a good introduction to phase equilibrium, this form of Raoult's law is not generally applicable to everything that you'll encounter in real life. That will wrap it up for this video. In the next video, I'll talk about how to find the dew point and the bubble point temperatures and pressures.